That's right. I have to speak English. I forgot that. And I use the microphone maybe. Okay, good. Yeah, this is going to be like a time series forecasting time series, mostly, not only forecasting, because you can do many things with time series. But anyway, the main type of data we're working on in this course is time series, which is a sequence of data observed over time. It's probably one of the most popular, I would say, data you can find everywhere. And they have their own characteristics. Of course, they are different from like cross-sectional data sets, because the memory of the past is always present in this data. And so much of our concern is how to exploit this memory to predict new data. And we have like the course is kind of divided into two parts. The first is the larger, the second is not as large as the first one, because you know most of the techniques we're going to apply on time series when we moved from linear models to machine learning and so on. So the first part, in some way usually you're less acquainted with, is the part about linear models, which in time series analysis are still very competitive. They are surviving like the deep learning revolution, because they often tend to work very well, especially because time series often are not that long, so you don't have so many observations as in other type of data sets, okay? And for example, even if you have like daily data, well, daily data is 365 observations per year, which even if you have 10 years, it's 3,600 observations, which is not that much for attacking the problem with deep learning and so on, okay? So usually the dimension of the data tend to favor simpler models. There's exception, of course. There are situations in which you have many observations. In this case, I mean, deep learning can also play a good role. There are specific deep learning models for time series that may work, but you need a lot of observations. Just to make a more, I would say, point example about this problem of the number of observation, especially if compared to the complexity of what you have to learn, or your model have to learn. Think about Easter, okay? Easter vacations, for example. In many time series, of course, Easter vacations are an important feature to predict data in that period of time, especially in social time series, so economic, sociological consumption of energy, and so on. Probably for any machine learning algorithm to learn the rule of Easter, you probably need 400 years at least. Okay, because it's very complicated. It's not based on the sun calendar, which all the rest is based, but it's more based on the moon calendar, which is not a feature that usually you have in your time series. So if you want like Easter vacation to be learned from a time series, probably you need 400 years of data, which you never have, okay? At least social data. Yeah, of course you have like sunspot data you have for maybe for 400 years, but not social data. And that's why linear models are still a very good player in this world. And linear models are also good, not only because they work, but also because they make you think of features that you may then want to use also in a linear model. So For a statistician, as I am, machine learning is just non-parametric regression, okay? So non-linear, non-parametric regression. And you can use non-parametric, you can supply non-parametric regression or machine learning features that are very well built. And learning linear model will also learn to build features that are good for forecasting, okay? So I would say 2/3 of this course will be on linear models of two kinds that I'm now going to explain to you. I would say 1/3 in using machine learning models, which you mostly already know, because actually you've also seen deep learning models for time series. For example, most of you I know have seen long short-term memory networks. Or not? Am I wrong? Have you already seen long short-term memory networks or GRU networks? Well, anyway, we'll go through those anyway. But most machine learning model you already know. You just have to learn how to apply them to this kind of specific data, which are time series data. Okay. Machine learning, yeah. So machine learning models just have to adjust what you already know to this kind of data. Linear models of the two kinds we're going to learn in this class are probably things that you've never seen. And so that's why we need to spend a little more time. And usually they're things that work very well. In computational, they're much, much lighter to compute than machine learning models. So that's not a good reason, especially if you have to implement your models into something that works in real time, okay? Okay, I think everything is set up here. So what about the examination? Because that's usually the question that comes in the first lesson in the audience. So the exam is divided in two parts. The first part is just written, old-fashioned written part, where you answer into the space that I give you. So usually no more than one page. So usually half page or something like that. But mostly with formulas or something, also drawing something. There are 5 questions, a little bit more theoretical, okay? And now it's, I would say, meaningless that you look at all the examinations because probably you don't understand them yet. But you will be, I think I already published some of the old examinations on the website, on the e-learning website. So you can just see what kind of questions, I mean, they're similar questions every time. So it's not, so learning those questions, learning how I reason about those questions is not hard. And then there is I wouldn't call it a real project. It's just more like something closer to a hackathon, I would say, where I will provide you with a time series data, which are not yet there. I still have to pick this year data. And you have to write a short report covering all the models that we are going to do. So you will have to write or to build an ARIMA model. So the first class we are going to use is this ARIMA model. Some of you probably coming from statistics may already know them. Then there is that's called unobserved component models or state space models, which is the second class of model, and you have to provide also a model of this kind. And then any machine learning model of your choice. So you will have to apply maybe 3 machine learning models to the data set, pick the one that is more promising, and then on the report, you will write the whole process, okay? So also the pre-analysis of the data set, maybe you will have missing values and you will have to fix them and so on. How you identify the ARIMA models, how you identify the UCM models, and which machine learning models you build and then apply them. So comparing, of course, with a training and a test set, all your models. And then you submit your prediction of a part of the time series that you don't have in your data. If there's a feature, I will give you the feature. Something there are no features, because something you predict the future of a time series that's using the past of the time series, or feature that you generate, okay? And so I will just tell you which is how long you have to predict, what is the format of the data you have to submit, and that will be, I would say, like the hackathon part. Okay? Which is, it doesn't really matter how well you do, as far as you do good models, from at least from a practitioner point of view. Okay, so if you're the first or the fifth, okay, it doesn't matter. But it's more, I mean, it puts a little more interest in the examination, and I will try to keep the ranking of your submission updated. Maybe not every day, but as soon as I can. And all of this starts, well, I would say, like 10 days before the exam. I mean, the submission. I open the submission like about 10 days before the exam. And you have to send your short reports like 3 days before the examination. So I can give a look at this. Then you have to present that report in front of me and your colleagues in about 10, no more than 15 minutes, okay? That's about how the examination works. It's not a big project, just time series, try different models, build these models in a proper way, and just document that in your submission. That's it. Okay. Questions? No questions? Okay. So I'm not sure what are your other courses they are following. Please just tell me if there are moments where we should like begin 15 minutes after the official time or end 15 minutes before the official time. I tend to be like more flexible to manage that. If I see that in a lesson you're getting too tired, then maybe I will end up earlier. But if you need, I mean, if you're coming from another building, for example, to this lesson, I just leave 50 minutes at the beginning. So if you have any of this kind of problem, just mention them so we organize the lessons in this way. Otherwise, I'll just come here as you saw at the beginning. Yeah, I see there's my colleague that comes a little bit longer. So, but anyway, I tend just to stick to the official times. It may be just, I don't know, but Friday they're kind of stupid times because there's always like lunch inside of it. Oh, look at it. So I think Friday we have, okay, this Friday I'm in a congress, so I'm not be here. So this is the only Friday we're skipping. Otherwise, yeah, I would say it's 3:30 on Friday till 6:30. So probably we can just begin at 3:30 and end at 6. So it's you have more time if you have to take trains and so on. Okay. So, and today I'll just keep it this way. Maybe I see if Gianluca is always ending up at a very last moment, maybe we just come 10 minutes later. Let's just learn from experience. I'm not sure how long he's going to do his lessons. But anyway, so no questions. So I'll just try to explain you a little bit of. I mentioned with the program, just to be a little bit more specific about this. See if it works. It doesn't look to work. It looks like we're on different. Great, it's not working. And I will try to share. Well, I'll just change the name, please. So I told you the first part, well, first we'll just begin to reason a little bit about the time series. The definition of a time series, the time we're going to work on, because of course there are more types of time series. We'll start playing around using R. As I told you, it doesn't matter if you then prefer to work with Python, you can find all the things we are doing R on Python. And then we'll just try to think of time series models for forecasting using what you already know up to now, okay? Just to jump into the problem. So today we'll just take a time series that is already in the data set of R, and then we'll just try to use our knowledge to try to forecast it, okay? But then the main thinking about the first part is talking about stochastic processes. Because we will see actual time series as a realization of a random object such as stochastic process. And particularly we will deal with stationary processes, with integrated processes, which are the processes that seem to to capture the features of the time series that we usually see in nature or in economics and so on. And from this word, we move to ARIMA, which will be the first big class of models we're going to use. ARIMA are in some way, well, you have to identify ARIMA models in a very handcrafted way, okay? You can, of course, try with automatic modeling. For example, in R, there's an auto ARIMA function that tries to find the best ARIMA model for your data. Well, it's very easy to beat that function, okay? So we'll learn how to properly identify ARIMA models, and unless you have hundreds or thousands of time series to forecast at once, usually reasoning on the time series and on tools that we learn to use allows you to build better models than automatic tools, okay? Because we know more things than these automatic tools, okay? Then we move to, an observed component model. CM, in which something that you may have already heard of, the state space form and the Kalman filter. Are the most important tools to apply them. Even though actually also the ARIMA world makes use of the Kalman filter, but in the implementation. And as I told you, this part will occupy about 2/3 of the hours. And then we'll just use machine learning and also deep learning for casting. The nice thing about ARIMA and observed component models is that we can do more things with time series than just forecasting, okay? With machine learning models, we would just do forecasting. It's nothing more that you can do with these kind of models. They're black box. Yeah. With ARIMA, but even more with UCM, actually, all of these UCM, we can do many things like extracting signals where interesting. For example, just to make a really simple example that you probably have encountered in your data line. You see that like official statistical institutes usually publish data raw and seasonally adjusted. So without the effect of the seasonality. Okay. So that's an extracting the filter, extracting a signal in some way. Because you're interested in the trend or the business cycle of the time series, but you're not interested in the seasonal movements, which are usually very huge, but they're not telling the story you're interested in. And then you would want to cancel out that part of the time series you're not interested in. Okay? So that's more like a signal extraction. Or for example, economists tend to work on business cycles. Business cycles is also a part of the time series. It's not the whole time series, it's a part of the signal. So it's a signal we want to extract from the time series. Okay? Sometimes we want to assess the effect, for example, of COVID on electricity consumption, or we want to assess how and I think about, for example that I put into the learning page. This is an example where we try to assess what was the impact of introducing the scoring system in Italy for drivers on the number of injuries on the roads. You know, in 2003, I think it was the scoring. It was in Italy introduced this scoring system where when you get a fine for moving traffic violation, you lose points, and if you come to 0, you lose your license for a while. Okay. So what was the effect of that? You cannot answer with machine learning this question, but you can answer with this kind of models. Okay. And the effect may be static, just on that month you have like a drop in the injuries, and then everything goes back to as it was before, but it can be permanent, like a lower number of injuries forever, or it can be a mix of the two. It can drop down, then come up, but not up to the same level of before, but maybe to a lower level. So then, and that's actually the case in that example. You may want to check it, maybe not now, but later. Or the effect of 9/11 on the number on passengers of flights, for example. So all this, seeing what happened under certain conditions, you can do using this kind of models. It will be very complex to do with machine learning models because they're like kind of over parameterized. They have many parameters and not so many observations in these kind of problems. Yeah, so basically this is what we're going to do. Any questions? I guess you're all acquainted with R. I don't think I do, but anyway, if you have a problem with R, just stop me. Because we'll do theory and application in the same place. I don't like to split the two things in different lessons. Usually, when I explain something, then I want to apply it right away, because theory helps application, of course, but application also help understanding theory. So we'll be doing both. If you have any problem with R, just ask. We'll be using like base R. We'll be using the KFAS package for state space models. Which stands for common filtering and smoothing, which is a good package for doing this kind of things. It's a good compromise between a completely automatic thing that does only the thing that he wants you to do, so that like more like simple to use, but not so complete as not so flexible as other. Like a full state space control, so full control of the state space system. So you have full control of the state space system in this package, but there are also like help functions that makes easier to work with the kind of models we're going to do. So you have the good of both worlds. So flexibility if you need it, simple of use if you use models that are pretty standard. The only thing with respect, for example, to more automatic models is that all the parameters here have to be estimated using numerical maximum likelihood estimation. So like starting values we have to manage. So there are not like automatic starting values in many packages you may have used for other models. And we cannot just set them random as you do in neural networks. Usually you have to reason a little bit about the meaning of each parameters in order to give a sensible value. And yeah, we must be using this. Okay, then you can use, maybe I will be not using that too much, but there is a forecasting package by a professor of Monash in Australia called Heinemann. And there's also, you probably have seen, if you go through my learning page, there's also a link to this web book, so it's available on the web, which is very much about applications, about being able to, so there's not much theory. He covers ARIMA, he doesn't cover UCM, covers like visualization of time series, outlier detection and imputation, so on. These kind of things, so seasonalities detection, and so on. So I would say it's a very good starting point if you start just going through this book. It's short, it's very application based, and he makes a lot of use of this forecasting package that he wrote himself, which has nice graphic features, has again a plethora of models you may use. So just it's something that you may want to look at and use maybe while writing your report. And that thing for me. I don't know if you're acquainted with the tidyverse world. So this kind of dialect that you have in R, which has become almost part of R. Maybe, I'm not sure, maybe with some data would be useful to use this SQL-like way of working with data, but it's really not necessary. Maybe and if you don't know that, I can explain you how it's working. It's very simple. But if you don't know this tidyverse world, you should get into it. It's really, it's like the main dialect of R. So it's not part of R, but it's almost part of R. It makes working with data really simple. And also, for example, the ggplot has much better looking graphs than the regular base plots in R. Yeah, I don't, if there are no more, if there was no questions. If you interact, that would be great. I mean, if we just speak, it would be pretty boring. So I hope you interact. You can come with your own time series if you want. I don't want the lessons to be too close to a high school lesson where one speaks and the other listens. So yeah, in any way we can interact. If you want to propose data or problems to attack me, but of course they have to be time series kind of problem. Just to make lessons more interesting. Okay. And maybe we can also do, I can, for example, a few months ago, they asked me to do a very simple thing, but it's simple if you know this word, of course. It's not simple if you're not acquainted with this. They asked me to do a kind of, it's usually called poll of polls, like political polls, where you had, for example, there was, they asked me for that for the European elections, okay? European Parliament elections. Many polls for parties, there were Italian parties, And you have many institutes that do their own polls, like they had 40 institutes doing polls for the Italian parties for these elections. And of course, they wanted like a real time, so streaming in some way, measurement of what was the most probably percentage of votes for each party, which was in some way using all the information available from all polls. Of course, polls, they are not every day. They're not synchronized. Some institutions do it on one day, and other institutions on another day. So there are not many missing observations, for example. But they want like a daily signal about this. And using these instruments was extremely easy to do that in a sensible way and a precise way. So maybe we can also just do that as an example. I have those data. I can give it to you. I just put it on the reader. Just they built, of course, a website which you can be able to recall. Just to show you, you probably already have in mind what that is. But just package, but there are also yeah. So every single point you probably not see. Okay. Something like that. So every single point you probably not seeing it, but you can just dial the address if you see that. But anyway, it's not that important. But anyway, any point there is a single institute. So for example, this is for these parties, the single institute saying on that day I got 22% for this. Now there is not the name of the institute, but are a bunch of institutes here, like 40 of them. And so what's the best way to build kind of the expected value? Well, we can reason about that in the proper way, okay? And using these instruments, we're going to see it's really some. I think I did this in a couple of hours. And then there are other, for example, at this very moment, I'm working also with €1. It's like MediaMarkt, like a big retailer of electronics, to optimize their investments in advertising. It's like you have like 9 different channels you can use for advertising: TV, radio, press, Google, and many other funny names they use. And you want to optimize, so get the best results in terms of revenues, okay, by spending less. Okay, that's the problem. And of course, you have also revenues for, I think, 18 different sectors, like 9 offline sectors and 9 sectors of their online shop. Okay. And also, so you want to maximize, actually they put targets on every sector. So you want to reach all these sectors targets by spending the minimum amount of money possible in advertising. And I use those models. Well, I use a complicated form of state space models because you have to model the response of the euros you invest in every channel of advertisement on every sector, so the revenues of every sector. So you want to know how much I get in revenues if I invest 1, 10, 100 euros in television, Google, and so on. Okay, so you have to be like a response model. Both in, you have to estimate like the shape of the response, which is probably an X. If you invest too little, you get a very little amount of revenues more. If you invest too much, you're probably saturated, so you are investing too much because from their response is usually considered like an S function, a sigmoid function. So you have to estimate that, and of course you have to keep in, the data that they have for this work are weekly, and so the advertisement of this week probably spills over also to the next week's. Okay, and so you also have a dynamic part. So you have to think that the investment you do now is affected this week, but also next week, and probably 2 weeks after that. So all this. Again, these kind of problems you can manage with this kind of models. Okay? Just to give you a range of there, those simplest models you will see also in examples. Well, not simple, simpler than these. Okay, they don't have to be that simple. Then, for example, we'll do some exercise on electricity loads, so demand, and also electricity prices forecasting. They're hourly data, for example, so more high frequency. And as you may think, electricity loads, so the quantity of electricity we're using, has many seasonal patterns. Why does it have many seasonal patterns? Well, there's a 24 hours pattern. We use more electricity in the day than in the night because we sleep, it's simple, and also because factories and businesses are open on the day and close in the night. Of course, we use more. So and this is the 24 hours pattern. Then there is a 7 days patterns because we use more electricity on working days than on holiday or weekend. Okay. So there's 7 day patterns. And then of course there's 1 year pattern because in winter there is less light, so we have to turn lights on earlier. So we can use more electricity in winter, but in July, for example, in Italy, everybody turns air conditioning, or actually June already. And so actually the peak of consumption is on July. But then in Italy, we go all on vacation in August. It's probably the only place where in August it drops everything so strongly. And so you see this peak in July because of air conditioning, but then all the factories close and everybody goes on vacation, and then you have this drop in August. So we have within here seasonality, which depends on, well, nature, the fact that the Earth is turning around the sun, but also habits. We go on vacation in August, it's habits, it's more, and of course calendar effects like holidays and bridge days. So if like the holidays on Tuesday, you take Monday off, that's like a bridge. So just to start thinking about what kind of problems we have to face and to model when we want to forecast or extract signals from time series. So that's a classical. So we have trends. Usually we have trends. The time series have the tendency to grow up and to go down. Some time series have like seasonal patterns, like business cycles. If you work with economics related time series, you have the business cycle. What's the business cycle? Well, economy goes up, goes down, goes up, goes up. Okay, over the trend of the economy. And then you have all these forms of seasonal patterns, which, yeah, if we have like monthly time series, it's really easy to adapt this 12 months pattern. But you have like hourly data, as I mentioned before, for loading time series. Well, then you have to think of features, so a feature that we want to build to model all these seasonal patterns, and the patterns may even influence one with each other, because the within year pattern of electricity consumption influences the within day pattern in electricity consumption. Because just for the fact that in summer, well, we're not in summer anyway, but in summer you have long days, so lights goes off maybe 5 in the morning, and they goes on maybe at 9 in the evening. Well, in winter, lights go on maybe off on 10 in the morning and go on 4 or 5 p.m. And so, of course, that means that the within year pattern of seasonality is influencing the 24 hours pattern within the day. Okay. So this is just, we will of course then get back to all these problems and cover them in lessons. But just to give you a big bunch of problems we have to deal and to solve in order to model time series. And of course, as I told you, Easter is particularly, I mean, it's not complex for us to model Easter because we can predict how Easter works because, I mean, there's a deterministic way to determine when Easter comes. But, for example, an automatic model, machine learning model, even a deep learning model, is not able to learn the Easter rules just for 2 or 3 years of data. I thought probably you need 400 years in order to learn Easter with a new deep learning model. Okay. Well, that was just like what we will be doing in this course. No more, actually. Any question? No question. Okay, then I'll ask you questions. Let's just start putting hands on some data. I just want to start with some data before doing anything about theory, okay? I want the data to pose us the problem. Also, because here, one basic problem is just forecasting. So we don't have to define the problem. It's forecasting, okay? And we will see later other problems, but let's just start with the problem of forecasting. I want to do that. So R already has some time series inside. We can just use the default data. So if you work with time series anyway in your, I would say, university lessons, you probably met the so-called L01 time series or air passengers time series, and just inside R. So that's why I want to use it just for an example to start with. And you can just, the nice thing is that you can just call it. Okay, it's called air passengers inside R, and in some way, well, it's very small. Probably you should connect to the streaming anyway. I'll zoom, and then I'll just try to maximize this here. Yeah, so. I don't think I can get it larger than this. Oh, this is bad. Okay. So this is the famous R passengers or R-line time series, which was it's famous because it was in the first book, which kind of organized all the information about ARIMA modeling and make them really practical. So it's a famous book that came out. The first version of the book is 1970, so it's pretty old. And if indeed this time series end up in, I think in 1960, yeah, it's 1960. And yeah, it was one of the time series used in examples in that book. And book, it's the famous Box and Jenkins book. Sometimes ARIMA modeling is even labeled Box Jenkins models because that book kind of organizes all this information. Of course, there's been much more research in the 80s and 90s, so that's not the end of the story. But I mean, was most of the story. So ARIMA models are not that new. There are even older models that are still in use. We're not going to see them, but for example, you can find them in the forecasting package by Heinemann, also in the book of Heinemann. They're called exponential smoothing models. They're even older, they're from the 40s. You can even compute them with a pen, okay? They're from the 40s, so or the 50s. So they mostly had pens to do computations. But anyway, it doesn't matter really how old are the models if they were, okay? So what about this time series? So this is a monthly time series, so 12 observations per year, every month is the number of passengers in thousands traveling on US companies, airlines. And two questions. What are the main features you already see in this time series? And the second question, how would you make a forecasting model with the information you have up to now? I mean, you're in your last year of university and you probably worked with data at least 2 years, but probably, well, at least 1 year, but probably much more than that. So the first question, what are the features you can see here? And the second question, how would you build a model for this time series to predict it, just to predict it? Just speak. So be shy. Yeah. So yeah, okay, it's going up. So it's trending. We can say there's a growing trend, and that's of course true. And that's something that we have to deal with if you want to predict that in the future. Then what are features? Did you see that? Or characteristics, if you don't want to use the word features because you use it for variables. Is there any seasonal pattern here? Of course, every 12 months, it's pretty natural. People traveling July and August in the US much more than the other months. So yeah, there is a seasonal pattern, but the seasonal pattern, what is the seasonal pattern showing? I mean, look at the seasonal pattern at the beginning and the end of the time series. So what's changing in the seasonal pattern? Yeah, it's hard to say it's increasing because it's a seasonal patterns. I mean, in the average should be zero because I mean, otherwise would be a trend if it doesn't not sum to zero every 12 observations. Okay, well, approximately sums to zero every 12 observations. But yeah, it's moving more and more. And probably the relation is with the trend. I mean, the higher the number of passengers, the more deep is the movement of the seasonal components, right? So these are the main features of this time series, of course, the one that one can see here, so just by looking at the plots. How do you predict this time series? You just with the knowledge you have up to now. Or maybe let's do this other game. How would you predict this time series just using linear regression? You have no clue? Suppose you're working for me and I ask, okay, I have this data, predict them for me, just 1 year, the next year. And you didn't follow this time series or streaming data measurement time series analysis course. You're working for that company. The company said, I need prediction for the next year. You're the data scientist. You have to do it. Sure. Yeah, You have ideas to do that. I'm sure you have. Don't be shy. If you're shy, this class is going to be boring. Sorry, it's the fact. It's just how it is. I mean, the components. He was thinking about a trend. How do you model the trend? So as human beings, we tend to think naturally of time series as having more components. We're talking about the trend, we're talking about the seasonal component, the business cycle, which may have also the fact here, it's hard to see. So as human beings, we tend to like automatically split the time series in these components. And that's why also we use sort of component models, because actually they're a good way to reason about time series. So just if you want to use linear regression, at least predict the trend, like a line that goes through the data. What would you use? How would you manage to use that, to do that? Really no clue? I'm sure you're smart in that. You just show it. What kind of trend could you use? Oh, I mean, a trend is just a smooth function of time, right? A line is very smooth. A polynomial is very smooth. So there are many functions, like deterministic function we can use to approximate the trend of this. So linear function, well, linear probably is not that good because it looks like it grows more, I would say, at an exponential rate than a linear rate. So we could use the exponential rates, but it would be non-linear in the parameters, or we can approximate it with a polynomial, maybe a second degree or a third degree polynomial would be good. But another thing is that we don't have to work on this very time series. We could even transform the time series. And there are good reasons to work on transform time series because we prefer to have linear models and possibly Gaussian models. We're very happy with Gaussianity and linearity. So time transformation would make time series that don't look linear, like this one. Why it doesn't look linear? Well, the trend is not linear, it seems more exponential. The seasonal pattern is interacting with the trend because it moves more the higher the trend. So the higher the trend, the higher is the variance of the seasonal component. So this is a nonlinear kind of function. And there are many transforms. We will see a class of transforms that are usually called Box-Cox transforms. You probably met them elsewhere. You can just Google Box-Cox transforms and Wikipedia will give you right away an answer of what they are. But a very special transformation, which is part of the Box-Cox family of transformations, but that we use a lot, is the logarithm. Why the logarithm? Because logarithms make absolute thing relative. So what does that mean? For example, if we compute, for example, the difference between 1 month of 1 year with respect to the same month of the previous year. If we compute that on this time series, we will have an absolute value, how many more travels on airlines have taken place from the same year of the previous year, the same month of the previous year to this year. But if you do the same exercise on log, so first you take the log, and then you compare this month with the same month of last year, then you have the rate of growth or approximation of the rate of growth. So the power of the logarithm, we will see more about that now and also, I would say, for the whole course. But the logarithm transform absolute changes in relative changes. And if you, for example, remember what's the derivative of the logarithm, it's the derivative of the function divided by value of the function. So it makes changes relative. Okay, so Just to show you this, let's say the log, I just call it Ly, so the log of y. And y will be our time series to predict in general, okay? So that's why I call it log of y. So look at this time series. Well, first of all, now the trend seems to be much more linear, of course, because if you look exponential in the original matrix, if I take the log, and if I take the log of an exponential, I get the linear, okay? So the trend is much more linear. Maybe it's a little bit less than linear, but it's not really a problem at the moment. So we made an exponential trend a linear trend, which is good. But even better than that, if you look at the seasonal patterns, now they're not expanding anymore because the logarithm makes the changes relative. And in this case, we saw that the variance of the seasonal component was in some way proportional to the level of the time series. But if you take the log, these changes become relative changes. And if they are proportional, then they will become just linear. Just to make you a better explanation about that. In some way, I would say that the higher line time series is a multiplicative time series. So a multiplicative time series is a time series that, if you think it in components, you have the trend that multiplies the seasonal factor and maybe multiplies the noise that, well, I'll just call it maybe N, like the noise, okay? So this is like the trend, this is the seasonal component, and this is noise. If you look at the original R passengers time series, maybe it can be thought as this kind of time series, because it's just like the seasonal component is kind of amplifying the movement of the trend. Like when the trend is high, the movement of the seasonal component is high. And that's a multiplication by rule. So, for example, if suppose we start with a trend at the level of 100, and that's the seasonal component, for example, for July, which is the highest month there, you have to multiply the level by 1.3, so it's 30% higher than the average July. But if I multiply 100 by 1.3, I get 130, so 30 more. If I go ahead in my time series and I go to 1000, for example, the value now is 1000. If I multiply 1000 times 1.3, now it's 1300. So I changed by 300, not by 30. Okay. So in a multiplicative model, the seasonal component is kind of amplifying what's going on in the trend. Okay. And the same is doing the noise component. So if the time series is low, the random component that every time series has is more. But when I get very high numbers, then I may think also the noise is higher. Okay. So a time series with these features, which look like the original air passengers, may be thought as a time series which is a multiplicative kind of pattern. But if you take the log, the log transforms multiplication into summations. And so you get that log of y is equal to the log t plus log of s plus the log of nt. And if, for example, if this was an exponential pattern, if it, like an exponential, so if we could model this using an exponential function. So what's an exponential function? It's the exponential e times the parameter to estimate on the data times the time that is. This way, we're building an exponential trend. Okay, but if I take the log, well, the trend is just now it's just theta times small t. Okay, because I took the log of e an exponential theta times t. Okay, and this will be this was like this would be like a factor, so something that is 1 point something if I have to amplify the level of the trend, or maybe 0.9 something if I have to take a little bit more down. Again, if you take the log, then you kind of approximate just the, I would say the, let's call it this way. This would be 1 plus some small numbers, epsilon that can be positive or negative. Well, then, if you take the log around 1, this is similar to the epsilon, okay? And this is just a noise. Usually, on positive time series, you have like a noise that has this shape, and then if you take the log, you make it more symmetric, so more closer to the Gaussian world. So that's just to show you why the logarithm is something that is often used, especially in positive time series. Okay, but the main thing that we notice right away is that it solves the problem of the seasonality growing in variability together with the trend. Okay, and this happens if, as I told you, there is like a linear relationship between the level of the time series and the variation of them. For example, the standard deviation. We can, for example, try to compute this on this very time series. If there is a kind of linear relationship between the level of a time series, so the local mean of the time series, and the local standard deviation of the time series, then the logarithm would solve this problem, the problem of the variability growing together with the trend. And why is that desirable? Well, in a linear world, as the first models we're going to use, it's more linear. So it's more, if we are using linear models, we want something that looks more linear. Of course, if you use machine learning, you don't have to care much about these things. You have to care about other things, because machine learning models are nonlinear. Okay, but if we stay in the linear world, we will do for 2/3 of this course, then we have to make the time series look more linear. Okay? And then model the transformation using linear models. Okay? Basically, this story. So, for example, if we go to our time series, how can we understand, for example, if, I mean, looking at the original plots, there will be a day in which you look at this and in 1 second say, I have to take logs. Okay, so this is basically how you will become after working a while with time series. But anyway, how to discover if the logarithm is a good transformation for your time series? As I told you, we can like inquire the relationship between the level of the time series and the variability of the series. And how can we do that? For example, we could take over every year. So we have 12 years. So compute over these 12 years for every year the mean and the standard deviation. And then plot these 12 points on the plot where we have the mean on the x-axis and the standard deviation on the y-axis. If these points look kind of linearish, they don't have to be on a perfect line, of course. But if they look linear, then the log will solve all your problems as far as variability connected to the level of the time series. Okay. So, for example, I'm not sure if you're acquainted with the time series object in R. So R has already inside in the staff package, which always get loaded, a TS time series object, which is a report object for time series. But it's okay if you have like quarterly or monthly time series, it's fine because it's thought having a slower index, which would be like the year, and a periodic index, which would be the seasonality index. Like for monthly data, you have the year and the month. For quarterly data, you have the year and the quarter. Quarterly means you have 4 observations per year, okay? And so on. If you have more complex data, like daily data, you have to throw, I mean, you could use the TS object, but it's not able to manage all the seasonality and so on. So there are packages with other time series objects. Probably the most popular, it's so-called XTS, so it's for extended time series. And there you can store any kind of dating of the time series freely. You can just, for every observation, you just can set the date or the date and time. So for more complex time series, we would be using the, I forgot to mention that, usually we will use the XTS package. It's for extended time series. There are other ones. There's Zoo. There's one which is called time series. So they are all packages. They're all okay. They tend to work the same way. Fortunately, the way R is built with generic functions and so on tend to make all the specific function to work very similar. But XTS, I think, is now the most popular, so we would be using that. Okay, but with this kind of data, we can just stick to TS, which is the internal. And what I want to show you is how the time part of the time series is managed in TS. As you see, practice, it's a number, it's a real number. Actually, it's a fractional number. The year is the first month of that year, and then it adds 1/12 to every next month. So, for example, so January is 0.0, the first month of the year. February is 0.083 because 0.83 is 1/12. Okay? Of course, if you have quarterly data, you have to sum 0.25 for quarter, yeah, and so on. So that's basically how the data is organized in this very simple object time series. So it doesn't even use a date object, okay? It just uses numbers. Why I'm showing you that, just so you can understand how plots the data. That's fine. But for example, for doing what we want to do right now, so computing from every year of the time series, the mean and the standard deviation, that's very useful because we can just group the year by taking the floor of that date. What's the floor? The floor is the integer part of the number, okay? So if we take the floor of those numbers, we just get the year, okay? Of course, if you use more complex date objects, there will be function to extract the year, the month, or whatever. But in the TS objects, which is very simple, this is how data are built. So we can just take advantage of that. And so I will build like a vector of the means. And I'm not sure if you know the function tapply. You know, probably you know the apply family of functions in R. They're functions where function has to be applied to a sequence of data, or in this case, to the data grouped into subgroups. Okay, it's like a group by, and okay, and t-apply, it's like table apply. I think you pass just in this case the air passengers time series, which is the data you want to summarize. Then you have to pass the indexing vector, and in our case we will just pass the year because it's grouping where we want to group the data by year. And so if we do flow of time of air passengers, we will just do the job. I'll just show you this part here so you understand how it works. You see, taking the floor just just takes the year of the observation. This is a vector. It doesn't matter. It's shown as a matrix because it's just the way plot works on a TS object, but it's just a vector. Okay? And then we have to provide the function we want to use, so mean. So this is taking the mean of air passengers grouped by this year, okay? So we do this with means, and we do the same thing with standard deviations. Okay. So if I plot, so the X are the means and the Y are the standard deviations, I see that I get something which is very close to a straight line. Okay. And this is telling you take the log difference, at least if you want to work with linear data. It may be convenient also if you work with nonlinear models, but especially if you work on linear models, that's the way to go. And if you have no linearities here, then there's a bunch of transformations. The Box-Cox transformation, which is a class of transformation which actually includes all the powers and the logarithm. And it depends on the parameters, which is usually called lambda. If this parameter is 0, then you get logarithm. If this parameter is another number, you get net power. So if it's 1, you're not doing nothing on the data. If it's 2, you're taking the square. Just to be quick, as I told you, it's a very popular tool in statistics. Well, this is already a complex version of it. So this is Box-Cox. So it's y, so the time series, the power of lambda minus 1 divided by lambda. Of course, if lambda is different than 0, this is just the power and then some kind of scale adjustment. But in linear models, changing the scale or something, that doesn't really have any significant effect. You just scale your model. Why do they do this? And they don't just take y at the power of lambda to get the logarithm, because if you take lambda and as a limit you push it to 0, the limit of that is the logarithm of y. So we have a family of transformations which is continuous with respect to lambda. Why is continuous with respect to lambda important? Because if you want to optimize using like numerical optimizers, you want usually continuous functions. Because numerical optimizers, they work well with continuous function, with what behavior function. Okay? So that's why they wanted a function of the data which is continuous in lambda. And the limit of lambda going to 0 is the logarithm of y. The limit of this function for lambda going to 0. Okay? So this is the family of Box-Cox function. You will see that, for example, in this forecasting package, the forecast package, there is a function that automatically estimates lambda using two different ways. Maximum likelihood, Gaussian maximum likelihood, and another way is general. So there are functions out there that kind of give you an estimate of lambda. But anyway, since the logarithm is the most interpretable transformation because it makes everything relative, then it's also the most favorite transform. Of course, if the optimal lambda is 0.2, okay, so if your aim is purely forecasting, take 0.2. But 0.2 is pretty close to 0. If you take 0, you get the interpretability of a logarithm transformation. And just to go on, okay, looking at this plot, we say, okay, our time series, if you want to address the problem by linear models, we have to take the log. We solve this problem with the log. And you can check it. You can check if we do the same thing with the log of the time series, we kind of don't see this relation anymore. We see it very quick, very weak. So I'll apply the same thing. I call it everything with L, like log. And here we have like Ly. I can just keep the rest equal because it's the same dating. Oops, means deviations. Okay, there's still a little bit of tendency to grow, but if you look at the numbers, they're very close to. I mean, it goes from 0.11 to 0.15. It's much more spread out. Okay, it looks like it's fine now. See, there is not really any more strong relationship between the mean and the standard deviation. Okay. So this is pretty fun. Good. As I told you before, from an interpretation point of view, the logarithm makes every change a relative change. And that's also interesting. For example, if we take the difference, the called seasonal difference, what's the seasonal difference? It's just what I mentioned before. It's taking for every single observation in this time series, the difference with respect to the same month of last year. So it's taking YT, in this case, minus YT minus 12. So the same observation, but 12 observation before. The same month, but 1 year before. So if you do that, you can use the diff function in R and do the plot. Of the log transform time series, you get this. Sorry, this is not the seasonal difference. This is the standard difference. So this is the seasonal difference because we have to specify that we want to take the difference with respect to 12 observations before. Okay. So if you look at this time series, first of all, the seasonal component kind of disappeared. Of course, if I take the difference with respect to that same month of last year, the seasonality tends to disappear because I'm comparing with a month which tend to be similar to this one, not to the previous month, which is very different usually from this one. But to a month is similar to the one I mean. So the seasonal component is almost cancelled out. Okay, but even more important for what I told you before is that these numbers that you see on the y-axis, they're relative changes. So if you see like a value which is like here, I should use this. So this is for example, this big peak right here, it's about 0.25. What does that mean? It's 25% higher than last year, the same month. Okay. So that's why logarithms are nice because they make changes, relative changes. And it's very easy to prove why that happens. It's not exactly the relative change, but it's a good approximation of it. If you, for example, work in finance, I'm not sure how many of you are acquainted with finance. In finance, you call them continuous time returns. Because it's like it's a change where you take all the infinitesimal times between now and 1 year ago, and you sum them in. But anyway, if the changes are not that huge, they are not very different than the typical rate of growth, which would be yt minus yt minus 1 divided by 1 yt minus 1, or yt minus 12 in case of these kind of differences, okay? And all we will see the coefficients of regression we are going to do also have this interpretation as relative changes. So that makes things also more interpretable. Is it muting? Oh. Okay. So going back to the log, the time series, which is this here. Oops, this here. So now we're in the condition to build a linear model. Now, somebody of you just tell me how you would predict this time series. So this is the original time series in logs. It's much more linear, so it's easier to attack the problem using a regression, linear regression. So how would you predict this time series? What kind of regressor would you use? Let's just reason on the components. How would you model the trend, which is pretty much linear? What kind of feature would you use? Variable. Really no ideas? What if you work it for something and predicted this time series? You have really no clue on how to attack the problem. Well, the simplest thing to do, what's a trend? It's a smooth function of time. If it's a linear trend, it's just a linear function of time. So building a model for the trend is pretty easy. I just can build like t, or if you want time, I'll just call it t. And we just build a vector with t going from 1 to y, the length of y. Oops, L01. Okay. This is just a counter. Well, the time is just counting the passing of the time. And if a linear trend is fine, I just pass this as a feature. If I want a more complex time trend, like a polynomial time trend, I just pass t, the square of t, the cube of t, to my regression, linear regression model. Okay. So, for example, the first regression was reg 1. I just want to model the trend. I built my counter of the time. So I regress Ly on, sorry, I need a tilde because I don't have a keyboard with a tilde. I think I just tilde from the have. You have a tilde, so you can just here. Just tilde from here. Okay, we call t the time, so that's just a, or we can do summer. So I just estimate a regression of the time series on the time. So this is the intercept. So what means intercept? Well, it's the value of the trend. In this case, the value x time 0, which we started to count from 1. So time 0 would be the last month before, I think 1948 was the last year. Would be time 0 would be December 1947, whatever. Okay, and that's the value of the trend. Then we have, you see, the coefficients for t is 0.01. What does that mean? As I told you, the log makes everything relative. So that's the increment every time 1 month is incremented, because we use as unit of measurement of the time the months, so 1 month to time. So that's the relative increment from 1 month to the next month. So the average increment is 1%. Okay, and this kind of rates of growth, differently from the classical rate of growth, which is multiplicative, this is additive. So we can say that the rate of growth on the average over 1 year is about 12%. You can sum them up. There are rates which are, as I showed, they are continuous time rates, so they're a little bit different than classical rates. They're approximating each other, but this thing is that, as I showed you, every month on the average, this time series increases by 1%, 0.01 is 1%, and over the year increases by some 12%. Okay, and that's the trend. And if I want to see how it looks like, we can do that. With the mouse. Well, I could see like this. So we can plot, for example, the original time series. No, the log time series. Sorry, together with oops. The fitted values. We just have a problem now. And the LM function doesn't preserve the time series object. So this is just a vector. So the prediction, which is called fitted values, is just a vector without date. So it wouldn't plot here because it doesn't have the same datum. So if we want to plot them together, we either transform this into a vector or transform the other one in a TS object with the same datum, which is pretty simple. We can just apply the TS constructor and say that so the first date would be I think it's 949 or 48. I think in 949. Month 1, and the frequency is 12. I think it's and maybe I'll just color it red. Okay, that's it. So what we have done right up to now is just modeling the trend of this time series using a straight line. Easy. Okay. That's, I mean, in my head, that would be the easiest thing to do, at least for the trend part. Then we have the seasonal parts, of course. Nobody of you had thought to do that, really? I mean, it's really the easiest way to think of modeling a linear trend. Of course, we can also try a quadratic trend if you want. Why a quadratic? But maybe if you look at the end part, it looks like the time series is slightly slowing down with respect to the linear trend. So maybe a quadratic trend would allow for that. Okay. But it's just something that I slightly noticed on the last values. Okay. And anyway, if you look at the R square, just with one feature, we already explained 90% of the variance of the whole time series. Of course, trend was the first thing everybody was noticing. He noticed that as the first feature of the time series. So if we explain that, we explain mass of the variance because it was evident that it was strongly growing. The other very important thing that one sees is that there's a lot of seasonality movement, seasonality patterns. How do you build regressors for seasonalities? I'm sure many of you have seen those. Have you ever done econometrics in your past life? Nobody has done econometrics? No? Nobody's coming from economics. But yeah, but it didn't do econometrics. Because in econometrics, they usually use so-called seasonal dummy variables for modeling the seasonal component. Is everybody acquainted with what a dummy variable is? Dummy variable. Okay, in the jargon of machine learning, it's one hot encoding. Okay. If you take the name of the month, for example, of the time series, you do one hot encoding of the name of the month, you get dummy variables, seasonal dummy variables. So you have one variable for January, and it's 1 when it's January, and 0 on the other months. Then there's the dummy variable for February, which is 1 when it's February, and 0 otherwise, and so on. So one hot encoding of the month would be dummy variables for the months. You never seen such things, right? You do have. Okay. They have a problem though. Well, first of all, we cannot use 12 dummy variables because they're collinear with the intercept. If you sum all the dummy variables, you come up with one, a column of ones, which is the intercept. So you have perfect collinearity with the intercept. So usually you use dummy variables. That's one. So if you have like 12 months, like here, you just use 11 of them. Times it. Okay. Maybe we can just stop here and we talk about dummy variables, variation on the dummy variables, and then other ways to model seasonal patterns, which are better for high frequency data. But anyway, yeah, you are not very interactive. I hope that gets better in the next month, in the next lessons, because it gets boring. I mean, it's boring for you, but also for me. I have to talk with human beings. But anyway, the takeaway, apart from the program, is that maybe you can try yourself, and then you have 1 week because we see on Monday. Just try to add dummy variables to this model so that you also catch the movements, the seasonal components. Okay, and then we'll start from there. Okay, good. Then we see you on Monday.